Everyone, welcome to the P1 program. This lecture is called P108.1. Okay, so in this lecture we are going to discuss about the Newton's laws, right? Three laws of Newton and their implications. So beforehand I have to tell you that we have seen Newton's laws for a long time, right? So from the seventh grade itself that you have been seeing Newton's laws, three laws of Newton. So I'm not going to explain the basics from that far, but we are going to look at the implications of Newton's laws in a very what in a shorthand form and in an application level. So that's what I'm going to do with this lecture. Okay, so first of all, for understanding the different benefits of Newton's laws, and what does it tells us, right? What is the use of Newton's laws in our real life? And if you think about that, you can clearly see that if you have a you can consider an experiment where you have a box, right, in space, right? So there is a box in space and it is there, right? And you're a person and you have a spacesuit and all that, and you are going to push that box, right? So you are going to push that box with a force. So there's a force here from your part, and you're going to push that a box, right? So this box is going to move in this direction if it's pushed, right? So there is a motion with respect to that push. That force that you have imparted gave it a motion, right? This force, which is a push or pull, right? So the push or pull that generates motion is called a force, right? So that's a force. So the definition of force is that it is a push or pull that can change the velocity or position of a body, right? That's the force. That's a technical definition of a force. Now when you push this box, it is going to move with a velocity, right? The box will be at some time t, it will be at a point which is distant from this origin, and it will have some velocity, right? So there's a change in velocity with respect to the time for this box. So that's the implication of that experience of a force. Now force, coming back to force, we will come back to force, and before that I want to look at this historically. So the first historical understanding of this force or this thing is that Galileo, right? Galileo have, in fact, the first person who tried to understand this force was that Galileo. He said that if the body is moving with respect to some in with respect to some force, or as a basis of some force, then it is going to achieve some velocity. If that's so, then that force must be proportional to that velocity. So Galileo said that force must be proportional to velocity because the force is actually making the particle move in some velocity. So higher the force, higher will be the velocity. So that's the logical thing that Galileo did, and it's actually very logical. You can clearly see that if you apply higher force onto the body, right? If you apply higher force onto this body, then it will go faster, right? So it will go faster with a higher force. That means it clearly has a direct implication. A force has direct implication on the velocity, and that was his process, right? We need to understand all the thought process just to know how valuable it is to go in the right direction. So F must be proportional to velocity was the idea of Galileo, and he said that the proportionality can be balanced, and it can be said that there is something called mass, and so F must be equal to mv, right? So force must be equal to mv, and the proportionality constant here is mass. Mass is the amount of substance present in a body, right? So mass is the amount of substance present in the body, and you can measure it, and we have discussed it in the first lecture itself, right? First part of the lecture. So the next person who came in the 16th century, he was born, and Galileo was 100 years earlier to his period, Newton, right? So Newton came in and proposed this idea is to be wrong, right? This idea of F is equal to mv is wrong. Because why is it wrong? Because why? How can you prove that it is equal to wrong? It is wrong. So you can say that F is proportional to uh, v is what Galileo proposed, right? So what is wrong with that thing is that if you are moving, right, with the mass, right, a body is moving under the influence of some force, and you have a velocity, right, you have a velocity and it is moving, right? So you move in this direction. After say a billion years, right, billion years, you'll find that body moving in the velocity, right, in the same velocity if possible, because it is in space. So you have to be little bit more imaginative here. So in space, when you impart a force, it will continue its state, which is a law, by the way, Newton's first law, which we will discuss right now. And before that, so if you go further and further, you can see that this body has to maintain this velocity in space, right? So if that's the case, then you can clearly see that if it has to have some velocity here, that means it has to have some force here, because force is proportional to velocity. So if the velocity, if there is some velocity here, then there must be some force here. So it is impossible for it to exist with some velocity without an existence of force, because force is directly proportional to velocity. Whatever the velocity there is, there must be a force, the proportional force acting on that body at each time to maintain that velocity, right? That's a big thing for you guys. That's a big breakthrough that Newton had found out, right? So it made it a revolutionary concept. So what corrections can you make to this equation to make sure that this doesn't violate this principle? So Newton came up with this idea. Newton said that Newton said that F must be proportional to not velocity but change in velocity, right? So it's delta v by delta t. That means, what does it mean is that if you have a box and you're applying force to it, so it doesn't give it velocity but change in velocity. So change in velocity after some time will be given to that body for some delta t, and the velocity will change to a new velocity, say v2. If it was v1, v1 plus delta v is equal to v2. So if that's the case, then we can clearly see that after some time it will end up with a new velocity, and that velocity, if it is not changing, there is not change in velocity in that case, then there is no force. That's the real case scenario, right? In a real world, that's what exactly happening, right? So there is, if there is no change in velocity, then there is no force. So that's more intuitive and more correct to the situations. So that's a basic thing that Newton did. And he said that, so he retained the value of the proportionality constant, which is the amount of substance present inside a body. So you said delta v by delta t. That's what Newton said. Now what you can get out of this is that these two are vectors, and so F must be equal to delta v by delta t is actually m times dv by dt for t tends to delta t tending to 0, limiting case or a generalized case. Or you can say F is equal to m times x double dot, right, x double dot, or F equal to m times a, acceleration. So force is equal to ma. This is the Newton's second law, and we will come back to this law, because I have to go this way, because this is historically correct. Okay, I have to be historically correct, and that's the reason why I went this direction. So now what is the implication is that Galileo thought that force was proportional to velocity. That means if a body has to be given some force, then it will move in this direction, and after some time you have to be constantly pushing on this body to keep it in the same velocity, right? In the same velocity, if it has to be maintained, then you have to give the force which is the same at all times, right? But in Newton's case, when you give a force, there is a change in velocity, you can call it delta V, and that change in velocity is retained even after the force is removed. So that's the direct purpose and idea behind these concepts, the different concepts. So I think you agree with me that even after 1 billion years, right, the force will be the same, the velocity will be the same, right, even without any actual force. That's the real case. Now that's right, there is the idea. And now what I'm going to give you is the first law. Okay, first law. So we have already said what the first law is, because what we have done is actually the first law. The first law says that every body continues in its state of rest or uniform motion unless impressed upon by it by an external unbalanced force, right? If a body has a velocity and it is moving in this direction, it will tend to move in this direction unless at some time point there is a force acting on this body in any direction, right? Any direction, and it must be unbalanced. Unbalanced means the component of the force on either directions is not equal to zero. In the opposite directions, the components of force is not equal to zero. That means there is no cancellation of force, there is an actual force present, and if that force is there, then this body will change its velocity, right? So every body continues in its state of rest or uniform motion unless compelled by an external unbalanced force impressed upon it. So you can clearly say that first law is telling us that it will remain the same if there is no interference of any force. So you can say first law gives you something called the inertia, right? So inertia is this tendency of a body to be in the same state even after a long time. So that's inertia. Now that's the first law, right? With the first law there comes some things, right? Inertia is there. Okay, let's see what else is there. So there is a mass, there's a mass of the body, and it is impressed upon by a force, and there's a velocity of this body. If force is higher, velocity will be higher, right? If force is smaller, velocity will be smaller, right? So that's the direct evidence of applying a force. Now we can see that for different mass it will be different. So if mass m1 and 2, you have two bodies m1 and m2, and you can clearly say that if m1 is greater than m2, right, for the same force you will experience different velocity, because the velocity for the same force, velocity of v1 will be smaller than v2, right? So because if it's a heavier mass, then the body will move in a smaller velocity. This is an experimental fact, right? So if that's the case, then there is some kind of quantity, right? Some quantity that is giving, that is taking in the force, right? Some quantity is absorbing the force and converting it into some physical factor that moves the body, right? So this body is maintaining its velocity, but the velocity is distributed based upon mass, right? So mass is dependent on this velocity. Now we can actually see that, so we have to make sure that the force has an instantaneous value, right? The force will have some instantaneous value on this distribution, right? The force will have something that is instantaneous right there. It is right there in within this body, but you cannot see it without measuring both mass and velocity, right? You have to measure both mass and velocity to understand the force's implication on a body. So you can clearly say that some part which is called the moment of force, right? Moment of force is called upon by P. So moment of force P is equal to m times v. So this is called the innate effect of force on a body, which is the moment of force or momentum, you call it. This is a vector because velocity is a vector, right? This is called the moment of force. Now what is interesting about this is that you can derivate the differential of P with respect to T. That means you are finding the slope of P versus time graph, right? So if you find the slope of that, or you find the function, the time rate of change of momentum of a body, that's what it is. So after a body having some velocity, after some time, what will be its change in momentum, P or mv? So m1 v1, afterwards sometime t, what will it become? M2 v2, right? So the change in that must be equal to, you can take the differential derivative with respect to t on the other side, you get m dv by dt, so that is equal to ma, right? So this dp by dt is equal to ma, and this ma is the time rate of change of momentum, right? Time rate of change of momentum of a body is called the force. So this is called the Newton's second law, right? So the second law is says that, right? So you can understand this in this kind of a way. You have a body which is at rest and it has a mass, and you given a force, and it will achieve some velocity v2. So you can clearly see that force will be m times v2 minus 0, which is the velocity, by t2 minus, if it was t1 and t2, 2 times t2 minus t1. So that will be the force, right? The force will be the change in momentum. So it will be change in momentum with respect to the time. So it will be mv2 minus mv1, right, by t2 minus t1. That is force, right? So that's the change in momentum, p2 minus p1, right, by t2 minus t1. So that's a basic representation of momentum and force correlation, right? Momentum is the instantaneous impact of a force, right, on a body. What are the component of force it has on a body? Now that's the second law, and you can you have something else, right? We have some one more thing, which is dp by dt. F is equal to dp by dt. So you can say f dt is equal to dp, right? In a general case, you can say f times delta t will be equal to delta p, right? In a generalized form, you can see that this is called the impulse, right? Force on a time range is equal to delta p, or change in momentum, which is equal to m times delta v, is actually called the impulse, right? The change in momentum impulse on a time range is called impulse. A short burst of force is actually an impulse, right? So that's an impulse called. So that's something is also a direct correlation with this second law of Newton. Now the coming to the third law, right? The third law says that if there is a mass m1 here, and you apply a force to it, and it will move with the force, right, with the momentum. So the momentum dp by dt is equal to force. For us, time derivative of that will be the force. So it will move with the component of force, right? It will move with the component of force, but it is stored in as momentum, right? You have to measure mass and velocity to understand the momentum, and the change of momentum with respect to time gives you the force, right? So this is at rest initially, and it will move with the velocity v then, and it is going to hit another particle, right? So that's what is going to happen. So m2, right, some other mass, it is going to hit m2, and when it hits, the third law says that f1, right, this is f1, which is the force of first particle acting on the second particle, and F2, which is the second particle's response to it, right? So F2, which is the second particle's response to it in this direction, will be the same but in opposite direction, is what the third law says. F1 must be equal to minus of F2. Okay, why is this true? Is it logically correct to think of it this way? So maybe I'll I'll convince you with a demonstration of a real life experiment. It is not a derivation, it's a demonstration. So you can see that two bodies moving with different velocities, or if it is m1 and m2 is going to m1, if m1 is going to collide with m2 and it is going to move, right, velocity. So m1 has the velocity v1 and m2 in the initial state, right, in the starting stage m2 was at rest, so v is equal to 0. Okay, v is equal to v1 and v is equal to 0 here. This is something before collision, right? So this is before collision. So before collision, these two bodies were sitting there, right, lying there, and it wasn't moving. The second one wasn't moving. So if that's the case, then we can say that the momentum before collision will be P1, which is equal to m1 v1 for the first particle, first mass, and P2, which is m2 v2 for the second particle, right, second mass. So this momentum is right there, right? This is the momentum. So the force imposed upon this body in the system, right? If you take this as a whole system, there is no other force than F, right? So if there is no other force, then F is equal to dp by dt, right? This dp by dt must be a constant, right? If there is no other force given to it other than the force I actually gave it to the first mass, then dp by dt, F is a constant, then dp by dt must be a constant, right? So if dp by dt is a constant, then p is not going to change, right? P is going to be the same afterwards. So P1 is the first body's momentum and P2 is the second body's momentum. Then you can say that P1 plus P2 before collision, this is the case of before collision, must be equal to a constant, right? Because there is no other force. Direct implication of Newton's second law, nothing more than that. So P1 plus P2 is a constant. This is called the momentum, conservation of momentum. So this is called conservation of momentum. So this principle is called the conservation of momentum. Momentum will always be conserved. If there is no, if you consider all the forces, if there is other forces, then momentum will be different, right? So this is a very natural result of what second law states. Now if that's the case, then this is before collision, right? This is before collision. What about after collision? So afterwards, it will, the body, after hitting the second one, right, second mass, it will this thing, okay, imagine this, you have a marble, a marble, and you hit it with another marble of the same mass. What happens is that you can clearly see this marble, after hitting, this marble will go in this direction and this marble may be staying in that same direction, right? So this marble won't will transfer the whole force to the second marble and this second marble will start moving. So this marble will be at rest and this marble will be at motion, right? So this is something that you have seen in your real life. So imagine that. So if you transfer this force, right, the force onto the second body, so the possibilities here are this body can start moving, right, or this body can remain at rest. It cannot go into this direction, it cannot go because we have applied a force in this direction. So this body cannot come back after hitting it with a force, right? Experiencing a force, it cannot come back to its original state, so that is impossible. Or come back to the direction opposite to the direction of force, it cannot be, it is not possible. When you throw something, it won't come back just like that unless there is some dynamics, like dynamics of air friction or something like that, which is forcing air, wind or something that force it in this direction of. So if there is no other force, then it must go in that direction, right? So it must go in this direction, so it is not coming back. So the second body what can do, and first body, second body can go in this direction, or it can stay still, right? The first body, it can have different options, which is it can go in this direction after collision, or it can stay still, or it can come back in this direction, right? So that's a possible. After hitting it could come back, right? So that's the three possibilities. So after collision, the momentum will be m1 v1 dash, which is p1, I'm assuming it to be. So v1 will be the velocity. It could be in this, in the right side or left side, or it would be zero. It could be zero, anything is possible. And p2 could be m2 times v2 dash, right? It will be changing. So that's velocity, that's the momentum. Okay, that's the momentum vector anyways. So what happens to after collision? So the momentum after is p1 plus p2 is equal to m1 v1 dash plus m2 v2 dash, right? So that's the momentum after collision. So I told you already, the momentum must be conserved. That means the momentum before collision must be equal to after, right? So you can say that v1 plus v2 before, which is m1, right there, m1 v1 plus m2 v2, right? m1 v1 plus m2 v2 must be equal to, so m1 v1 plus m2 v2 must be equal to m1 v1 dash plus m2 v2 dash, right? So that's the direct significance. Now I'm going to limit my case here. What I'm going to do is that I'm going to imagine that if a marble is hitting another marble, this marble comes to rest, and this marble gets some velocity and it will move. If it was in rest at the initial, before collision, right? Before collision this was at rest, and after collision this will become at rest. So if that's the case, then we can say that, okay, let's notch it up a little bit. This will be at rest, the initial part will be at rest after collision. So what you can say that is, the initial part, in the initial part m1 had some velocity but m2 had no velocity. Okay, so that must be equal to m1 v1 dash plus m2 v2 dash, right? So that's the case. So you can say that this is the case when initially v2 had no velocity, v2 is equal to 0. Now you can differentiate with respect to time, and you get dv1 by dt must be equal to m1 dv1 dash by dt must be equal plus m2 dv2 dash by dt, right? So that's a direct taking differential. So this says that m1 a1, which is the acceleration of the first before collision, m1 a1 dash, which is after collision, plus m2 a2 dash, which is also after collision. So the force will be imparted like this, right? Force will be imparted like this. Now if a1 was at rest, right, after collision, the first marble, the first box was at rest after collision, then you can say m1 a1 must be equal to m2 a2 dash. That means this means, what does it mean is that the force on a1 before collision is equal to the force on a2 after collision, right? After collision you can call it f dash, f2 dash. So this means that the force is completely transferred to the second body, right? The force is completely transferred to the second body after collision. So this marble came in and hit another marble, and the first marble with, this is before collision, and the first marble stayed there, this marble stayed there, this marble started moving with the same velocity as that of the first marble. That's what happened, right? This is the clear cut case of that. So this is a transference of force, right? Complete transference of force. So why is it something that signifies the importance of third law? Well, it is because that if you can imagine this. So if you hit something with a force like this and you hit another thing, and this force is impacted onto this thing, and the first box came to a rest, right? This came to a rest, and the second body is moving with the velocity which is the same, okay, which is the same of as that of the first thing. So if that's the case, then we can clearly understand that in this part, in the collision part where there is collision occurs, if you have to stop the body with the velocity and mass, then you have to apply some force which is F, right? So this force must be equal to the force it had to achieve this velocity and for this mass, right? So whatever that you have gave this mass to go in this velocity v must be the exactly what you have must have applied to stop this body to the velocity 0, right? So at the point of impact, or at the point of collision, you can clearly see that the mass when collide with the other mass will give the same force which is transferred across after collision, right? After collision, this force has to be given, exactly this force has to be given to stop, right? To stop this to a complete halt. So F must be equal to the response force, which is F of reaction force or response force. This is called the action force. So action force must be equal to the reaction force in magnitude but in opposite direction. So that's the understanding of idea of the third law of Newton. And this I have done all the best I could to explain everything in the most a logical way, right? Most logical and most mathematically possible way. I hope you guys understood this. This is very important to understand things in much more detail and on the basic route. Now, this is not a derivation, this was a demonstration. Well, experimentally, if you check this, everybody in this world satisfies this equation, this condition of transference of force and action reaction pairs. So that's why this model of Newton, and his laws are accurate, because it is experimentally verified. Okay, that's the final thing I need to say. Okay, so you can do one more thing which is called mass calibration. So in space, in space, what is an issue is that there is no gravity, right? If there is no gravity, then you cannot measure the mass of a body, right? So what you can do is that you can use the second law of Newton, and you can say, if you know the mass of something, say 1 kilogram, and you apply a force onto it, and then you measure the the acceleration, right? So if you measure the acceleration, let's say 1 meter per second acceleration, you gave some force, and so you can calculate the force now, right? So force is equal to ma, which is 1 times 1, that is 1 newton. The unit of force is newton, and the newton means kilogram meter per second square, right? So second square, so that's called 1 newton. So now you know the exact force that you have applied, right? And you then let it collide with other body in space, right? Let it collide, and what happens is that you have to conserve momentum. That means the force has to be transferred completely. That means the second body, when you know the actual force of this body, which is 1 newton, and you collide it with other thing, and okay, when you collide with the other thing, and you can measure the mass of this, the acceleration of these two things, right? You can measure the acceleration or velocity of these two things after collision, right? After collision you can find the velocity, and you can use p1 is equal to p1 plus p2 must be equal to p1 dash plus p2 dash, right? You can use that, and you can find the mass of the second body, right? mass of the second body. And maybe you can do it simply. If you can calibrate the force to some quantity, say 1 newton, and you apply it on a body, and you find that there is an acceleration which is equal to 1 meter per second square, right? So 1 meter per second square was the acceleration, or 2 meter per second square. Then you can say that the force I have applied is 1 newton, but the mass times acceleration was 1 m times 2 meter per second. So mass is just 1 by 2 newton uh, per kilogram, sorry, per meter per second square. So that is 1 kilogram, right? So 1 kilogram, so that's the mass. So you can calculate the mass, and this method of calculating is called mass calibration. In spacecrafts you can measure mass only using this method, because um, not there are some advanced techniques to measure mass, but the basic thing that you can use upon our knowledge right now based upon this course is using this method. Okay, so I hope you enjoyed this lecture. This is very simple, and this is very broad and easy, and much more important than any other thing that you will ever see in physics. It is much more important than that, I'll say that. So I hope you enjoyed it, and have a very good day. Thank you, guys.